Welcome to the Agrawal classes. I am Ajit Agrawal and we are studying thermodynamics for the first year engineering students. Today we will discuss about the reservoir and the heat engine, heat pump and refrigerator. A thermal reservoir is a hypothetical body with relatively large thermal energy capacity that can absorb or supply finite amount of heat without any corresponding change in its temperature is called energy reservoir, or we can say thermal energy reservoir. That means when we are talking of a reservoir, we say we are having a big source of energy where we are having a large amount of energy, and if we supply some small amount of energy to this reservoir, the temperature of the reservoir will not change. Temperature will remain constant. Or similarly, if we take out some finite amount of heat from this reservoir, so the temperature of this reservoir still remains constant, then we say it is a thermal reservoir. Then there are two types of thermal reservoirs. One is the source. We can say a source, a thermal reservoir, a source reservoir, when we are taking out a finite amount of heat and the temperature of this reservoir doesn't drop, we say it is a source. For example, if you consider, then the sun is continuously giving some amount of heat, but the temperature of the sun doesn't drop. In case of nuclear reactor also, the temperature remains constant. In case of an electrical furnace, the heat losses are continuously there, but the temperature of the furnace remains constant. So we can say them as a reservoir. If you consider in the other terms, here we are talking about thermal reservoir. If you consider for say water reservoir, if you are having a large dam where a large amount of water is there, and if you are taking out one bucket of water out, then the level of this dam doesn't decreases. So here we say this is as a water reservoir, or if we put one bucket of water in the reservoir, then the level of this reservoir doesn't increases. So we say this as a reservoir. If you consider some other example, say if you are having a bucket, in this bucket we are having, say up to this point we are having a water, and if we take out one drop of a water, then we cannot find any difference in this bucket level. Or if we put one drop of water in this, then also we cannot observe any change in the level of this bucket. So we say this as a water reservoir. So here when we are talking of thermodynamics, we say as a thermal reservoir, there is a large amount of heat. If you take some amount of heat from that, even then the temperature of this reservoir, or you can say a system, will not reduce. Then we say it as a source. Or if we supply some amount of heat to this reservoir and the temperature of this reservoir doesn't increases, then we say this as a sink. Say for example the atmosphere, when whatever the amount of heat we are rejecting into the atmosphere, but the temperature of the atmosphere doesn't increases, then we can see a sea. In the sea we are supplying continuously some amount of heat or some amount of water, even then the level of the sea doesn't increases. In case of river also we can say the temperature of the river doesn't increases, although it is getting some heat continuously. So we say this as the reservoir. These reservoirs will be more useful while discussing the next topic, heat engine, heat pump and refrigerator. Now let us consider the heat engine. These three are the very important topics for the thermodynamics, because these are the basic and these are all the time we are using in this thermodynamics. The heat engine is a device which converts heat energy into useful work when operating in a cyclic process. As we can see, in case of our petrol engine, that is a heat engine. because it is converting heat into useful work, and it is operating in the cycle and converting heat energy into the useful work or the mechanical work. We can represent this as, here we are having some source or a thermal reservoir of source type, where we'll take some amount of heat from this source. The temperature of this source remains constant, say the temperature is T1, and then it is supplied to a device. We say this device as a heat engine, which converts the heat supply to this into a useful work, and it rejects some amount of heat, say Q2, to another reservoir at temperature T2. And as it is receiving the heat, the reservoir temperature, that is the sink type, which is receiving the heat, the temperature of this reservoir will not increase. So this is the heat engine. Basically, it is a device which is receiving some amount of heat from a source reservoir at a temperature T1 and is converting some of that heat into useful work and rejecting the balance amount of heat to a sink reservoir at temperature T2. So if you consider this one, and this happens continuously in the cyclic process. So we are getting continuously output on this. If we apply the first law of thermodynamics, then heat supplied minus heat rejected is equals to work done. Because it is a cyclic process, so net amount of heat supplied to the system, that is heat engine is my system. So Q1 minus Q2 is the heat supplied, and that is equals to the work done. That is the from first law of thermodynamics. And if we wish to find out the efficiency of this engine, then we can simply write efficiency as the output upon input. So output we know as W, or we can write as Q1 minus Q2, and heat supplied to this heat engine is Q1. So this is the efficiency of the heat engine. So this can be written as 1 minus Q2 upon Q1. So that is the way we can find out the efficiency of the heat engine. Next we'll consider the heat pump. Heat pump. What is heat pump? Basically, heat pump is a device which is used to increase the temperature, or which is used to increase the energy inside that particular system. So in this case, what we are having a device which is receiving the heat from the source at temperature say T2, and when we supply some work to this device, it converts and rejects the heat or supplies the heat to another reservoir at temperature T1, where T1 is greater than T2. So this is the device which is used to heat up this particular system or the sink. Or if you consider this as my device, then this device is converting a low temperature heat, say Q2, to a higher temperature heat Q1 when we supply some work to this device, and this device is known as the heat pump. So here what we are interested, what is our output? So our output, or what is our requirement, is the heat at a higher temperature. So the output in this particular case is the Q1, and what we are supplying, so we are supplying W amount of work to run this. So this becomes the more than 1 in some cases. So we, instead of writing efficiency, we write as COP, coefficient of performance. We say it as a coefficient of a performance. So in this case, it is the you can write as useful effect upon the work supplied. So useful effect, when we are talking of heating or heat pump, so this is the energy going out at a higher temperature is our useful effect. So it is Q1, and to convert this low grade energy or the heat at lower temperature to a higher temperature, we have to do some work. So the work required is work supplied. So that becomes the COP. If you apply the first law of thermodynamics, net heat supplied is Q2 minus Q1 is the net heat supplied, and is equals to the minus W, because we are supplying the work into the system. So this is the from the first law of thermodynamics. Net heat supplied, that is Q2 minus Q1, is equals to the net work done by the system. So in this case it is on the system, so it is minus W. So this is from the first law of thermodynamics. So we can write as W is equals to Q1 minus Q2. So here if we substitute, then the COP becomes Q1 upon Q1 minus Q2, or 1 minus Q1 upon Q2. So that becomes the COP of the heat pump. Now let us consider a refrigerator. A refrigerator is a device which, while operating in a cycle, maintains body at a temperature lower than the temperature of the surrounding. That is in case of our refrigerator, or in case of our AC, what we are doing, we are keeping the temperature of the body or of our space lower than the surrounding. So here in this, when it is operating in a cycle, here it takes the heat from a lower temperature and it rejects it to a higher temperature body, that is the, you can say, as a sink in this case, and this is at temperature T1, and T1 is higher than T2. And while doing this, we have to supply some work to this device, and this device will be operating in a cycle. So it is the source. From this source we are taking heat, and then it is supplied to the device. Device is operated by the work, and then it converts this heat into a higher temperature and rejects it into the sink. So this is our requirement. We want to keep this particular at a lower temperature, and this is in the surrounding. So here say we are having a surrounding, and in this particular case this is our system we are having inside the universe. So what happens, as this temperature is lower than the outside temperature, heat is continuously leaking inside this system from different walls and different surfaces. So the temperature of this system increases, but we don't want to increase the temperature. So what we will do, we will take some amount of heat continuously from this system or the source, so the temperature of this body remains constant and it's lower than the surrounding. And as it is taking out by this device consumes some work and is converts into the higher temperature heat and rejects it into the sink. So here say the amount rejected is Q1, amount taken out from the system or the source in this case is W, and to convert this lower temperature heat into a higher temperature heat, we have to supply W amount of work. So in this case, again, what is the useful effect we are getting? So in case of refrigerator, useful effect is the Q2 amount. So the useful effect is the Q2 amount of heat. And what is the work required to take out this heat is the W. Work required or work done is equals to W. Again, this becomes to be most of the time more than 1. So instead of writing an efficiency, we are writing it COP, coefficient of performance of refrigerator, as equals to useful effect Q2 upon work done W. And if we'll apply the first law of thermodynamics for this device, the net heat supplied to the system is Q2 minus Q1 is equals to the net work done by the system. So it is minus W because the work is done on the system. So we can write as W equals to Q1 minus Q2. When we substitute here, the COP of the refrigeration is becomes Q2 upon Q1 minus Q2. So this is the COP of the refrigeration. When we had considered the COP of the pump, heat pump, we had written down as Q1 upon Q1 minus Q2. If we'll take both together, then we can say as the COP of the heat pump is equals to COP of refrigeration plus 1. By solving this, you will get, if you will add this in this 1, then it becomes the COP of the pump. So when we are considering these two, refrigeration and pump, you remember working is same, but only the useful effect is different. When we are considering the heat pump, the useful effect is the amount rejected into the sink at a higher temperature. When we are considering the refrigeration, its useful effect is the heat taken out from the lower temperature source. So that way it changes. So COP of the refrigeration Q2 upon Q1 minus Q2 and COP of the pump is Q1 upon Q1 minus Q2. And this relation you remember all the time, that COP of the heat pump is equals to the COP of the refrigeration plus 1.